So yeah, thank you for joining us. Today's talk is going to be given by Kiara Hansenne from the University of Saigon, and she'll be talking about deriving uncertainty relations from basic notions in graph theory and some applications of that. So yeah, whenever you're ready to start, you can begin.
Okay, all right. Can you also see my cursor?
Yes.
Okay, perfect. Well then, hi everyone. So first of all, thank you very much for the invitation. It's a pleasure to talk in this seminar. So yes, as I said, I'm going to talk about uncertainty relations and some notions of graph theory. So this is work that I did jointly with Carlos de Gois, who's a PhD student like me at the University of Siegen in Germany, and with Otfried Kühne, our supervisor. All right, so for those who maybe open the paper, this is a very short summary of what we did. So basically we have some observables, and then we can build some graphs depending on some properties of those observables. And then from the properties of the graphs, we derive some uncertainty relation like this. So this is mostly what I'm going to be talking about, and I'm going to go step by step to be sure that everybody understands and so on. And yes, I also wanted to say that if you have any question, you can please interrupt me at any time. Especially in online talks, it's nice to have some feedback. So yes, feel free to interrupt me anytime. Okay, so first I'm going to motivate a bit what we are later going to discuss as a problem. And then in order to solve this, so what we did in the paper, we are going to introduce some notions from graph theory. And then once we did all that, we will be able to go to the main result and then see how this result can be applied to different problems in quantum information. Namely, we're going to talk about entanglement detection that we can do using the uncertainty relations we just derived, and then see how those uncertainty relations can also be used to derive local uncertainty relations and entropic ones. And then when we're going to be done with all this, we will close with some discussion. Okay, so first I'm going to motivate a bit uncertainty relation in the problem in general. So we know that in physics, observables are physical quantities that can be measured. And in particular, in quantum mechanics, we represent them by Hermitian operators. And then those Hermitian operators have real eigenvalues, and each of those eigenvalues is a possible measurement outcome. As examples, we can talk about the position x and momentum p, but then those two observables, for instance, cannot be measured simultaneously with arbitrary precision. And how do we know that, and since when? Well, we actually know it since a long time ago, so since Heisenberg's uncertainty relation from 1927, which stated that the product of the variance of the position and momentum has to always be larger or equal to h bar squared over 4. And then since then, there are many other types of uncertainty relations who have been derived, and they also had some applications, so you can use them for entanglement detection. As I said, we're also gonna use ours for entanglement detection, but they also were applied to things like security proofs in quantum key distribution and other applications. But then this one here that I just presented is for two observables, so position and momentum. And we kind of ask the question, well, what happens if we have more than two? And actually, there are not so many results about uncertainty relations for more than two observables, or when they are, it's like only for qubits and so on. So it's like a valid question. So what happens if we have more than two observables? So now I'm gonna present the problem in more details. But then before that, I'm going to make sure that everybody's on the same page and talk about some very basic in quantum information. So we're going to talk about quantum states, which are positive semi-definite operators. Here will be noted rho, and that have a unit trace. Then we're also going to discuss about quantum observables, and as I said already before, those are Hermitian operators and labeled with some capital letters like this A. And we're going to talk about taking the expectation value of that Hermitian operator on a given state rho. So here's a expectation value of our observable A on the state rho is just given by the trace of the product of those two operators. And then we're also going to discuss about variances, which are defined like this. Okay, so what's the problem we are actually interested in? Well, given some set of observables, so we have a set of some observables here, and we are going to specify, ask that they square to identity, meaning that they have eigenvalues that are plus or minus 1. And what we are interested in is a lower bound on the sum of the variances of all those observables. So if you have n of them, you just sum all the variances, and we want to find the lower bound over all quantum states to have an uncertainty relation. But then in order to do that, we will define this quantity E that we will use a lot in this presentation, which is just the sum of the square of the expectation values of those observables on a given state rho. Then just by taking the definition of the variance, you can just expand this quantity that we had here. So what we were looking on a lower bound for, we just expanded, and then it's equal to n number of observables minus E, this new quantity. So from going to the search of a lower bound on this expression, now our main question is going to be, what is the upper bound on E? Meaning, what is the maximum over all quantum states of the sum of the squares of the expectation values of those observables? So this is going to be the question, so the bound on this E here that we are going to be interested in.
Hansenne, this is Bill Phillips. You didn't say anything about rho squared. Are we talking about or restricting ourselves to pure states, or does this include mixed states?
No, it also excludes mixed states.
Okay.
So it's for any valid positive semi-definite operator here with unit trace. So also for mixed states.
Okay.
Okay, so from this expression here, E, well, this has been studied before, and there are some known upper bounds on this for some particular cases. And here I have some examples. So for instance, if we take our set of observables AI, such that they all pairwise commute. Well, if you have n operators that all pairwise commute, they share a common eigenbasis. And then if you take any common eigenstate of all those operators, if you just evaluate the square of the expectation value, you're going to have 1 for each operator, and then it's just going to sum to n. So this is a trivial bound, meaning that if you have n pairwise commuting observables, the upper bound is just given by the number of them. Then another case that has been studied before, if they all pairwise anti-commute. So if we now have a set of n observables and each pair anti-commutes, then E is upper bounded by 1. And this is a bit less trivial to see, but if we go to an example, for instance, if you take the Pauli operators x, y, and z, those 3 pairwise anti-commute, so each pair of them anti-commutes. And now if you take the sum of the square of the expectation value, it is upper bounded by 1. And this, for those who know, is the upper bound on the length of the block vector of any quantum state. And this can be expanded. So for instance, if we take now an orthonormal basis of the space of all Hermitian operators acting on a d-dimensional Hilbert space, so now this E, so the sum of the square of the expectation value, is going to be upper bounded by D, so the dimension of your system. And this also can be seen as the bound on the length of the block vector for now a d-dimensional system. So those are examples of which for which we know a bound on E, but there are not many others. So for arbitrary sets, this is in general not known, an upper bound on this. Okay, so now we're going to go to the notions of graph theory that we need to derive our results. So first, we're going to define some quantities. So if we have a graph G, which is a set of vertices and edges. So for instance, if we have our graph here, we have 6 vertices and that they are connected by those blue edges here. And for those kind of, for graphs in general, you can define the clique number, omega of G, which is just the order of the largest complete subgraph of G. And then we can also define the chromatic number, and this is going to be the smallest number of colors needed to color each vertex of G, such that no connected vertices have the same color. So this sounds a bit arbitrary and complicated, but it's actually quite simple. So if we just look at this example here, for the clique number, we end up with 3. So omega equal to 3, meaning that the largest complete subgraph of the original graph that we have here is a triangle. So for instance, you can take that one. So it's fully connected. So each vertex is connected to any other. And its size is 3, meaning we now have a clique number of 3. So for the coloring now, the chromatic number is equal to 4, meaning that you need 4 colors to color the graph such that no vertex that are connected have the same color. And this you can just check. If you take any pair, you can see that if they are connected, they don't have the same color. And if they have the same color, it means that they are not connected. And those numbers can be computed. And so you need at least 4 color, and you can check that you cannot do this coloring with only 3. Okay, so in this example here, we have omega and chi that are different, so 3 and 4. But in general, well, for some graphs, those quantities can be equal. And actually, we call the graph G weakly perfect if those quantities are equal. Now, the clique number and chromatic number of graphs are NP complete problems for them to be determined. But there's an efficient approximation that we are also going to be using, which is the Lovász number of a graph. So now if we have a graph G, its clique number is upper bounded by the Lovász number of G bar, which is now the complement graph of G. So it has the same set of vertices, but then the edges are complementary. And this quantity is now upper bounded by the chromatic number of G, so the original graph that we had. So this Lovász number theta, it was originally introduced to bound the Shannon capacity of a graph, but in the end, it has been used in many different applications, and it's not always related to this Shannon capacity. For instance, like in our case now. And for some graphs, theta is actually analytically known, but otherwise, so there are many different definitions for theta, and they are all equivalent. And here I've shown, I've decided to show 2. So one of them here is so that we can notice that actually theta of G bar can be computed through a semi-definite program. So here this sounds a bit complicated and so on, but you can just check that it can be computed indeed by an STP, meaning that we have to maximize over a matrix with some restrictions here, the sum of the entries. And then here, this is going to be useful later, and that's the definition that we are going to be focused on, is if you take the Lovász number of a graph G bar, you have to maximize the largest eigenvalue of some matrix B with some restrictions that are listed here. And since we're going to use this, I'm going to go into some details and with an example so that we understand what it actually means. So if we take our graph that we had here before, so this wheel here with the clique number equal to 3 and still chromatic number equal to 4. Now we take its complement graph, so G bar, which is now this one. So basically any, so it's the same set of vertices, and then any 2 connected vertices in G are not in G bar and inversely. Okay, so now if we have this definition of Lovász of G bar, so the Lovász number of G bar, we have to maximize the largest eigenvalue of B with those constraints. So B is an n times n real matrix. So here, that one is this matrix B for this graph. So n times n being the number of vertices. So here we had 6, so it's a 6 times 6 matrix. Then you put ones on the diagonal, like this. And then we put 0 when, so the element ij is equal to 0 when ij is in G bar. So when I and j are connected in G bar. So for instance, here 1 and 3 are connected. So in 1, 3, you put a 0 and so on. So that means that in the end, you end up with 5, 0 on the lower triangle and 5, 0 on the upper triangle because we have 5 vertices. And now you just maximize the largest eigenvalue of this matrix with the constraint that it is still a positive semi-definite matrix. And then you end up with the lowest number of this G bar, which is equal to 3.236. And you can then check that it is indeed larger than the clique number of G, but smaller than the chromatic number of G. Okay, so that's it for the lowest number. And now that we know a bit more about those quantities, we can go to the main results. All right. So we go back to our initial problem, which was, just to recall, that we look for an upper bound on E, meaning that we want to maximize over all quantum states the sum of the square of the eigenvalues, of the expectation values. And then in order to solve this question, we define the anti-commutativity graph of a set of observables. So how is it defined? So if you have a set of n observables, you associate to each observable one vertex. So here the set of vertices is going to be 1 to n number of observables. So here I put an example. So if you have those 5 observables here, you associate to each observable one vertex. And then the set of edges are going to be, well, you connect I and j when the observables that you have anti-commute. So that's why it's called anti-commutativity graph. So for instance, if you take this observable here, so this is a short notation for Pauli operator X tensor identity. So I just wrote it like this so that it's a bit more compact. And then with this one, for instance, Z tensor identity tensor X, well, they anti-commute because X and Z anti-commute, and then all the rest commute. Then you just draw a vertex, an edge between, and then same for those ones and so on. And then when you end up with an anti-commutativity graph of the set of observables. Okay, well then, once we've defined that, what we have shown is that if you take a set of Hermitian operators that square to identity, so that I said already before, but we restrict ourselves to observables that square to identity, meaning that can only have eigenvalues plus or minus 1. Well, then the sum of the square of the expectation value is upper bounded by the lowest number of the anti-commutativity graph of our set of observables. So I'm going to just say that again. So if we have a set of Hermitian operators square into identity, and you sum the square of the expectation values on some given quantum state, well, then you cannot go higher than the lowest number of the anti-commutativity graph of the set of observables you had. And how we can see? Well, now we can go through a bit more details and see the proof. So for that, we defined a new observables E of rho. So this depends on some given quantum state, which is going to be a linear combination of the observables we had before. And the coefficients are going to be real coefficients, which are the expectation values on some given state rho. So this is still a valid observable because we have a real linear combination. Well, then you can just take the variance of this new operator, which can be expanded like this, and this is always larger or equal to 0 because it's a variance. Well, now we're going to go just rewrite those two quantities here. So the first one we just expanded, so we just take the definition again and expand it and so on. And then we notice that actually, if you take the expectation value of this product, all the imaginary parts are going to cancel out. Because if you sum over ij, well, the ji element is equal to the conjugate of aj element. So then since you sum over all ij's, well, all the imaginary parts are going to cancel out. And you can only restrict yourself to the real part of the expectation value of this product here. Okay, so then this can just be rewritten here, where I vectorize the small coefficient a and define the calligraphic a with as a matrix with those entries here. Oops, sorry. Yes, and then this is just upper bounded by the largest eigenvalue of calligraphic a times the norm of this vector a. Then for the second one, same, we just expand, and then we notice that actually those small ai coefficients are the same than the expectation values here. So we can just rewrite it like this. Then you have the norm to the power 4. And then since those coefficients are actually equal, we can just rewrite it like this. And then we have our two quantities here. And then we conclude that the sum of the square of the expectation value is upper bounded by the largest eigenvalue of a matrix calligraphic A with those entries. All right, so I hope everybody still follows. So then from this, what we just found, where we have the largest eigenvalue of this matrix with entries like this, it follows that this is always smaller or equal than the maximum of the largest eigenvalue of A, with the restrictions on A that are the following. So this calligraphic A matrix is n by n, because we had n observables, so the indices go from 1 to n. Then this is a positive semi-definite matrix. And how do you can see that? Well, actually, if you take a matrix whose entries are expectation values of product, this is positive semi-definite. And then taking the real part is also just still positive. So this still holds. Then we have ones on the diagonal. And this comes from the fact that we forced our observables to square to identity. So if you just have AI squared, you're going to have identity, and then expectation value is just 1. Okay. And then we notice that the element ij are going to be 0 when the observables anti-commute. And why is that? It's because if you take, well, the element ij, and then you just flip operator A and operator J, and since they anti-commute, you have a minus sign that appears there. But we have seen before that it's actually equal to the conjugate, meaning it's purely imaginary, and then taking the real part where only nothing stays, and we end up with 0. And now this has to remind you of the definition of the Lovász number of the anti-commutativity graph that I just gave before. So this is exactly the same form as we had before for the Lovász number of the anti-commutativity graph. And then from that, we can conclude that actually the sum of the square of the expectation values is upper bounded by the Lovász number of the anti-commutativity graph. Okay, so now that we have this main result, we can see a few examples. So first, we consider when we take a set of observables where all pairwise anti-commute. So if we now go to the anti-commutativity graph, since all observables pairwise anti-commute, you have to draw an edge between all the vertices, basically. And now if you take the Lovász number of this graph, well, the Lovász number of complete graphs is equal to 1. So you just have that the sum of the square of the expectation value is upper bounded by 1. And this actually is exactly the result I showed you before, that for pairwise anti-commuting, it's upper bounded by 1. Remember the XYZ example with the length of the block vector. Now, if we take the opposite of this situation, meaning that no of the observable is going to be allowed to anti-commute, we have an empty graph. So we have no edges because no pair anti-commute. And the Lovász number of an empty graph is just the number of vertices. So here it's going to be 5. Meaning that if none anti-commute, it is upper bounded by the number of observables. And then in particular, if you take them to all commute, so if they all commute, none anti-commute, so this holds. If they all commute, you just evaluate this on an eigenstate and you can reach the bound. And then another example here, if you have observables that have anti-commuting relations that look like a pentagon, then the Lovász number is square root of 5, and then the sum is upper bounded by square root of 5. So from if we now expand a bit some graph theory notions that we have, we can formulate some already known results in a very nice way. So this is some trivial bounds, meaning that if we now have a set of observables and we split it such that we have in each subset only pairwise anti-commuting observables. So if you have a set of, I don't know, let's say 20 observables, and then now you split them in 5 sets such that in each set they pairwise anti-commute, well then in each subset, the quantity E is going to be upper bounded by 1 because in each subset they're going to be anti-commuting. So now you can just count how many subsets you have, and then you have a bound on the original E for the original set that you have here. But then now, if you want to have the best bound possible, you just have to make such that you have the least subset possible. But then actually, if we analyze our if we analyze our anti-commuting graph again, we notice that the smallest numbers of pairwise anti-commuting subsets is actually given by the chromatic number of G, which is the complement of the anti-commutativity graph. And then now we have that the largest, upper bound on E is the chromatic number of the graph G, so the complement of the anti-commutativity graph. So this is just a bound that follows from the maximally pairwise anti-commuting bound. But what is interesting is that we have some graphs where the lowest number of the anti-commuting graph is strictly smaller than the chromatic of the complement. For example, if we now have the pentagon again, so this is the anti-commutativity graph, meaning the observables are going to have these anti-commutativity relations. Well, then the lowest number of this graph is equal to square root of 5. If we now take the complement, so the complement of this pentagon, this star here is going to be also a pentagon. The chromatic number of this graph is now 3. So we need 3 colors to color this such that no adjacent vertices have the same color. And you see that those quantities are, well, not the same. And this is nice because then it means that only having the bounds for pairwise anti-commuting observables is not enough. So you will have cases where the lowest number is going to give you a bound that is tighter than if you only consider the pairwise anti-commuting relations. So this was a very nice result, meaning that it actually is interesting to know the lowest bound because you cannot just take the chromatic bound as an upper bound on E, because then in some instances you won't have a as nice bound as if you take the lowest number.
Generally, you mentioned that it's easier to compute the Loveish's number instead of the chromatic number, right? Did you mention that? Okay, I see.
Yes. Also, so this one is so can be formulated as an ATP, and this one is NP complete.
Thank you.
Yes, so also an advantage to actually have that bound and not only the chromatic bound. But then the question that follows from this is the Loveich theta bound a type bound? Well, as we saw later, is that actually no, not always. So meaning that we found some examples where the Loveich number bound is not tight. So if we take now pentagon observables, so I put them here again. So these are the anti-commuting relations. We actually found that for those specific observables, we reformulated our problem such that we could formulate it as an STP. And then if we maximized over all quantum states with these observables, we found that the maximum you can actually reach with a quantum state is 2, which happens here to be equal to the clique number, which is strictly smaller than the Loveich number of G bar, which is equal to square root of 5. So another example is when you take the 27 observables of this form, meaning you have Pauli operators x, y, and z, and you take 3 tensor products of them. So for instance, you can take y, tensor z, tensor x, and so on. So all of them. You take all those 27 as a set, and then you can compute the Loveich number of their anti-commutativity graph, which happens to be equal to 5. Meaning that according to our result, if you sum the square of the expectation values, you have 5 as an upper bound. But actually, from other works, so in particular for works on sector length, it is known that if you maximize over all quantum states this expression for this set of observables, you can only reach 4. So this is already known. Again, happens to be the clique number, so you can start to see a pattern here. Yes, so here is again an example where the Loveich bound cannot be reached. And that actually holds for all sets of x, y, and z, and then tensor number n of qubits. And then we also have some other numerical evidences where the Loveich number is not a type bound. So this brought us to the following conjecture. So for the case where the observables either commute or anti-commute, for instance, for tensor products of Pauli operators. So our conjecture is that when those observables either commute or anti-commute, then the maximum over all quantum states is actually equal to the clique number of G. And now G here is the complement of the anti-commuting graph. And since now, if they don't anti-commute, the observables compute, this is now the commutativity graph. So the clique number omega t is the size of the largest pairwise commuting subset. So if in omega t you have a clique of, let's say, 6, then it means that you have 6 observables that all pairwise commute. Yes, so we have some evidence to support this conjecture. So the examples that I just showed you before, we have a lot of numerical examples, but we still don't know how to prove this, and we still haven't found a counterexample. So this is still open, and if you have any idea or whatever, then you can just tell us. So why are we actually interested in this particular case where they either commute or anti-commute? Well, it is exactly because tensor products of Pauli operators appear a lot in quantum information problems. And those operators either commute or anti-commute. And they appear a lot, for instance, in sector length, so that's just what I mentioned before, but also in stabilizer formalism and in many other cases. So this is a situation where they all either commute or anti-commute, where it would be very interesting to have a tight bound. So now that we been through all of this, so I showed you the main result and then the conjecture that we have and so on. I'm going to go to some applications of this and then first talk about some application in entanglement detection. Okay, so for that, we actually noticed that there's a simple connection between E and the separability problem. And I'm just going to recall what the separability problem actually is. So we say that state rho is separable if it can be written as a convex combination on product state. So you have an state rho here of the system A and the B, and then you can write it as a convex combination like this. And we say it's entangled if you cannot write it like this. So it's just entangled if and only if it is not separable. And then the separability problem is to if you have a state rho, to determine if it can be written or not like this. Okay, and then using our research, what we saw is that if you take any separable state rho prime acting on system A tensor system B, and then you maximize over all separable states, the sum of expectation values of observables that can be written as products. You can just rewrite this like this. And then using Cauchy-Schwarz inequality, you end up with something that looks like this. And then we see again here the sum of the square of the expectation values, what we just found an upper bound on. So now we can just use the upper bound we found and found that this is then upper bounded by the Lovász number of the anti-commutativity graph of the observables A and the one of the observables B. So now we have two sets of observables, and each set of observables has one anti-commutativity graph, and each set of observables has one Lovász number. So that's the one for the observables AI, and that's the one for the observables BI. Okay. And then from this, what we can do is we can build some entanglement witnesses. And what are entanglement witnesses? Entanglement witnesses are operators that are used to detect entangled states. So more formally, what it is so an entanglement witness is an observables W for which the expectation value is positive for all separable states. And it is negative for at least one entangled state. So meaning that if for some state rho the expectation value is negative, then it is entangled because it is positive for all separable states. So smaller than 0 means that it is entangled. And this has a clear geometrical interpretation. So if you have here the set of all quantum states and here the set of separable states, well, the entanglement witness W with this trait equal to 0 is going to be a hyperplane cutting the set of states into two, and then the part above are going to be entangled. So if below, I mean, if the trait is smaller than 0, this is going to be entangled, and then this is the part where the expectation value is bigger than 0, which includes all separable states. And why witnesses are nice in general in entanglement detection Well, first, it's because they are observable, so meaning you can actually measure them if you want. So if you have a lab and so on, you can measure the witness as an observable. And characterizing the set of separable states is a very difficult task in general, but then if you use some smart entanglement witnesses, you can detect some nice entanglement states. So this is something nice to have, and now using our result, we will be able to construct them. Because finding good witnesses is not easy in general, and many people have done works on that and so on. So it's nice that using our result we can do. So what we just showed before is that the maximum over all separable states of the sum of the expectation value is upper bounded by this expression involving the lowest number of those two anti-commutativity graphs. Well, then we construct the witness WE like this, which we can check is always larger or equal to 0 on separable state. And if we now choose some wise sets for A and Y and good ones for B, then we will see that we can actually detect some entangled states. Okay, so now we go to an example. So if we take the two q-quark entangled states, so we have the state here, which is the state of two q-quarks, so 8 qubits, and it is PPT entangled, so meaning we cannot detect it with the PPT criterion. Yes, so this is defined like this, and then you have some projectors and so on. It's a bit complicated to see, but actually, physically, it just means that you have some party A and some party B, and they share some probabilistic mixtures of Bell states. So this is basically how you can construct this state here. So now what we did is that we took two sets of observables, so the set A and the set B, and we took 15 observables for A and 15 for B. And then we computed their anti-commutativity graph, and they happen to be the same. So this is the graph here. I didn't write down the observables because they were yes, very ugly and so on. So I just wrote the anti-commutativity graph so that we have an idea. So these are different sets. So A and B are not the same observables, but they happen to have the same anti-commuting relations. Meaning that if they have the same anti-commutativity graph, they have the same Lagrange number. Okay. And then from those 15 observables, I just built the witness WE with the 3 that is the Lagrange number of A and B, and minus then the sum of those tensor products of the observables. And now we wanted to detect the state rho E, so this entangled state here, but we mixed it with some white noise, meaning that we have a probabilistic mixture of rho I and the maximally mixed state here. Then we just computed the expectation value of our newly found witness, and we checked when it was smaller than 0. And actually, for visibility larger than 3/5, we found that this is negative, meaning that this state rho here mixed with some white noise is entangled when the visibility is higher than 3/5. So that was actually a nice result because this 3/5 here happens to be exactly the bound for which it then becomes separable. So if you go below 3/5, then the state becomes separable. So meaning our witness here was able to detect the state, the full range for which it is entangled. Okay, so now that I've showed you some examples of entanglement detection, I'm gonna talk a bit about local and about entropic uncertainty relations.
Could I ask a question quickly about the witness?
Yes, sure.
So you mentioned that, okay, for in this case, it's sort of, yeah, I guess anything like after that bound, it's separable, so it's detecting it well. Is that, have you found that to be true for whenever you're using this kind of method to construct the witness?
Yes, so we check for several states and we usually get very good results, but then you actually then need to take some sets of observables that are very well tailored to your state you're trying to detect.
No, I see.
But yes, we have a few examples where we actually found the whole range.
Got it. Thank you.
Okay, so those local uncertainty relations, they can also be used to witness entanglement, and with the following method. So now we suppose that we have an uncertainty relation, which is a sum of variances larger than some constants, that holds for states for all states for party A. So this is then local because we now want to witness entanglement, meaning we have two parties, and then this one holds for just the party A, so it is a local uncertainty relation. Then we have the same thing for B. So again, an uncertainty relation that is local only on B side. And now we defined a global observable, Mi, which is just the sum of the extended observables here. So we just defined this set of observables. And it is known from previous results that if now minimize over a set of separable states, the sum of the variances, it has to be larger than Ca plus Cb, so those two constants. So this is results that are well known already before and were used to detect entanglement and so on. But as I said at the very beginning, in general, it's difficult to find uncertainty relations to start with. So in the first place, those are difficult to find. So now that we actually found one uncertainty relation, well, we can just use it and see what happens. Okay, so that's what I just said. So basically using the upper bound on E, we can just derive our new uncertainty relation here. So now we have that the sum of the variances is lower bounded by n, the number of observables, minus lowest number of the anti-commutativity graph. Yes, and then using this, we can now construct some nonlinear witnesses. So meaning we have our two local uncertainty relations, some on Alice's side and on Bob's side here. These constants, now we find them using our results using lowest numbers. And yes, so this is just what I showed you on the previous slide. If you now minimize over all set of quantum states, this has over all separable states, this has to hold. So by just rewriting these using the Lorentz theta bound, we end up with this equation here, which has to hold for all separable states. Meaning that if it's this expression here is smaller than 0 from some state, you know that it is entanglement. And then also what is known already before, what we can recover when the Lorentz number are actually equal. So for instance, for the witness that I just showed you, we had two different sets of observables, but they happen to have the same anti-commutativity graph, and so they had the same Lorentz number. So this sometimes happens. And so when those two quantities are equal, then these nonlinear witnesses, coming from the fact that we have here nonlinear term, are strictly stronger than the ones I showed you before, meaning that they will detect the same states and even some more. And now we can also build some entropic uncertainty relations. So what are entropic uncertainty relations? Well, it's uncertainty relations again, but that are based on entropies. And entropies only need probability distribution, meaning that in order to build an entropic uncertainty relation, you just need to know the probability distribution of your measurement results, and you don't need to know any expectation value or the eigenvalues of some observables and so on. So you actually don't need any of that. You just need a probability distribution. And that's why people like entropic uncertainty relations in general, because they are considered to be more fundamental, because they don't depend on the actual measurement outcome, but just the statistics. So that's for more like a fundamental level, but also they are useful because they were used in security proofs for QKD, randomness certification, and so on. So they also have some more practical applications. Okay, so now for our problem, we take the results of measuring our observable AI on the state flow, and we end up with some probability distribution here. So this probability distribution comes from the fact that the observables have eigenvalue plus minus 1. They square to identity, so that's why we have a probability distribution of this form. And we can notice that it only depends on the square of the expectation value here. So now, depending on this, we can we write our entropy of our distribution like this. And now, in the cases where S is concave in expectation value square, meaning that it is a concave function, over this variable, and as we saw here, it's the only variable on which our probability distribution depends. So we have a function S that will only depend on this parameter here. And if it is concave in this parameter, and for instance, it holds for Shannon entropies and Sadis entropies for some parameters, so meaning this is a reasonable assumption to have. And if the lowest number of the anti-commutativity graph is an integer, and this is also reasonable to ask because, for instance, for all perfect graphs, so meaning when the clique number and the chromatic number are equal, those are integers, and then the lowest number is also an integer because it's equal to those two quantities. Well, then we end up with this entropic uncertainty relation, meaning that if we sum the entropies depending on our observable and our state, they are lower bounded by number of observables minus lowest number of anti-commutativity graph time S0, which is just a probability, entropy of the probability distribution 1/2, 1/2. Okay, so using this, we now have an entropic uncertainty relation based on our anti-commutativity graph results. And this can be used to build steering witnesses. So steering is a type of quantum correlation, which is stronger than entanglement, but weaker than non-locality. So if you have here a set of entangled states, you have some that are steerable and some that are non-local. So all non-local states are steerable and all steerable states are entangled. So steering is a semi-device independent scenario, and it can implement similar protocols than non-locality, but it's easier to deal with in practice. And what is this steering scenario? So basically you have Alice on this side and Bob on this side, and they share a quantum state. And then Alice chooses a measurement depending on some input X, and she has a result A. And now Bob on his side, he does local tomography of his share of the state. And then what Alice and Bob share as information is an assemblage. So assemblage are defined like this. So this is a bit technical, but we won't go into the details, but this is the general setup of steering. So Alice measures depending on some input, and Bob does local tomography. Now we want to construct a steering witness using our entropic uncertainty relation here. And it's a bit similar to what we did with local uncertainty relations, meaning we have our uncertainty relation here that will hold for all dA-dimensional states. So it's going to hold on Alice's side for all Alice's states. And then for all unsteerable states of dA/dB dimension, so now we have states, global states for Alice and Bob. And for any set of n observables on Bob's side, then this has to hold. That the sum of the entropies is lower bounded by the same quantity here. Meaning that, so this has to hold for all unsteerable states, meaning that if it's violated, then you know the state is steerable. And since all steerable states are entangled, you also know that it's entangled. Meaning steering witnesses are stronger than entanglement because they detect states that are steerable, meaning that have stronger, which is a stronger requirement than just entangled. Okay, now that we've seen a few applications of the result we have with our uncertainty relation, I think it's time to finally wrap up a bit and then discuss. So to recap the presentation, what we actually wanted is to find uncertainty relations valid for multiple observables, which we did. So we found that in the case where observables square to identity, then the sum of the variances is lower bounded by n minus theta of anti-commutativity graph. So this is the main result that we get. Yes, and then we analyzed a few other graph properties, and we found some cases interesting, meaning that if the observables either commute or anti-commute, it seems that the actual tight bound is the clique number and not the lowest number. This is at least true for all perfect graphs. I forgot to mention that because for all perfect graphs where the clique number is equal to the lowest number, so it obviously recovers that conjecture. And then it also holds for at least some imperfect ones, which are the ones that I showed you as supporting evidence for the conjecture. And then finally, where I showed you some applications of our bounds to typical quantum information problems, for instance, entanglement and steering detection. So we're still interested in this problem, and we still work on this. And then the first obvious thing we're working on is to figure out what's happening with our conjecture. So is the click number really the tight bound for commuting case, or not? Or are we gonna find some counterexample at some point? So this is something we're still working on. And then something we would like to do is to see if we can extend our result to observables with more than 2 outcomes. Because there even a smaller number of uncertainty relations are known, and this is because it's very difficult. So yes, we would like to see if we can do something about it, but let's see. Then on the more practical side, what we would like to know also is to see what happens to our bound if our measurements are not perfect, meaning the observables don't exactly anti-commute, but something close. So that's on the more practical side. We would like to know how our bound evolves if we have something like this. Then also it was brought to our attention that in exclusivity graphs and quantum contextuality, the Lovász number also appears, and somehow we noticed this connection and thought, well, maybe there's something more about this. So this is also something to be investigated. And then finally, we're obviously interested in any application of the bound. And actually, this whole project started because in some entanglement in quantum networks or in network compatibility problems, we use the fact that pairwise anti-commuting observables have an upper bound of 1. And then we wanted to know if we could extend this bound. And then now that we have the result, we would like to know if it actually can be applicable also this entanglement in network problem. Okay, and then, well, this is the end. I would like to thank you for your attention. And then if you have any questions, please ask.
Thank you very much for your talk. Yeah, we can take some questions now if anyone has any.
Yeah, I have a question. Thank you. This was a really interesting talk. As far as other connections, it springs out to me that this seems similar to like the setting for like multi-parameter quantum metrology, where like you would like want to bound like similar to these uncertainty relations, right? Where you want to bound like the sum of some variances of, I mean, if I take my parameters to all be accessible via some set of observables. And there the known bounds are not saturable and hard to compute. And it seems like maybe one could use your relations there in that context as well. And I was wondering if you've like thought about connections like quantum Fisher information or multi-parameter metrology or any of that.
So I had this comment already. So yes, I heard this and so on, and would be interested in, but I didn't look into it at all for now. But yes, that's also some possible applications. Yes. But
Awesome.
then yes, I didn't look into it yet.
Well, I'll look into it a bit and I'll email you or something.
Okay, it's cool.
It does seem very directly applicable to me, but I have to think about it. But, yeah, but thank you. This was a really cool talk.
Thanks.
This is Bill Phillips again. At the beginning, you said, well, one of the motivations here is to try to understand uncertainty relationships for more than a pair of observables, and you certainly got that. Now, when we first learn about uncertainty relationships in pairs, we learn about the connection between the uncertainty product or the minimum uncertainty product and the degree to which the observables don't commute. Now, what I'm wondering is what you have shown in some sense a generalization of that, or is that too simplistic a way of thinking about it?
I mean, it could be, and that's why also I was quite surprised. So if I show this result again, oops, yes, this one here. So basically, here we see that only having the anti-commuting relations, well, yes, having the fact that you have pairwise anti-commuting observables is not enough. So somehow you need something more than just pairwise if you only consider pairwise commuting observables, your bound is not as tight as if you consider the whole set of observables. So this was something I was very surprised to notice. But
Yeah,
which is,
me too.
which is also very interesting. And then the fact that we took sum of variances and not products, this has been done before already. So people already started to consider sums of variances and not products. Because if you take the product as soon as 1 is 0, well, then you have a trivial bound. And if you have many, then it's not so nice to see. I don't know if this answers your question.
Well, sort of. I'm still a bit confused.
Are there any more questions? Yeah, I can also, let me actually stop the recording if anyone wants